Let's look at one more example here. I would like to sketch the graph of f of x equals x minus 3x raised to the 2/3 power. So I might start by looking at the domain of this function. Here I've got two separate terms. I can look at the domain of each one of those separately. The domain of x is not going to give us any issues. X is just a linear function. It's a polynomial. Domain of that is negative infinity to positive infinity. Negative 3x to the 2/3, though, on the other hand, you may have some concerns about that term. But remember, I can rewrite this as x minus 3 times the cubed root of x squared. As soon as we see this cubed root right here, we know that, well, everything inside of the cubed root function, or rather, I should say, that cubed root function is continuous so long as the part that's inside, which is x squared, is continuous. Well, x squared is continuous everywhere, which means that the whole cubed root function is going to be continuous everywhere. So the domain of this function is negative infinity to positive infinity. We're not going to have any issues with our domain here. Next, we might want to look at asymptotes. Neither one of these functions, whether it's a radical or a polynomial, have asymptotes. So we have no vertical asymptotes. We have no horizontal asymptotes. And that's everything I can say about my original function f of x. So let's talk about f prime of x. Let's find our derivative. Derivative of x, that's just going to be 1, minus, here I'm just going to use the power rule. So let's see, minus 3 times 2/3 times x to the negative 1/3. 3's will cancel. I'm left with 1 minus 2 all over x to the 1/3 power. Here's our derivative, f prime of x. Now you could leave your derivative like this, or you could get a common denominator. It's really up to you how you want to handle it. I actually think it's going to be easier to take the derivative of this, so I'm actually just going to leave this here. And I want to find critical numbers. I want to find places where my derivative, f prime of x, is equal to 0, and places where my derivative is undefined. So first I'll take my derivative, 1 minus 2 over x to the 1/3 power, set that equal to 0, and solve this equation. I'll add 2 over x to the 1/3, so I have 1 equals 2 over x to the 1/3. And I can't solve while that x to the 1/3 is in that denominator, so I'll multiply both sides by x to the 1/3 power. And what do I have? I have x to the 1/3 power equals 2. The way I would get rid of that 1/3 power, really that's a cubed root. I would cube both sides, or you can think of it as raising each side to the reciprocal power, raising each side to the 3/1 power. On the left-hand side, I'm left with simply x. And on the right-hand side, 2 to the 3rd, that's 2 times 2 times 2 should be 8. So x equals 8 is one critical number that we have. Next, I need to think about places where f prime of x does not exist. Here, this is, I'm worried about this, the denominator right here, this x to the 1/3 power. If that's 0, then the whole derivative is undefined. So I'm going to take the denominator, x to the 1/3, set it equal to 0. Here, this is a little bit easier to solve. I just need to cube each side. On the left-hand side, I have 0. On the right-hand side, that 0 times 0 times 0 is, well, just 0. So I have two critical numbers. I have 8 and I have 0. So we're ready to make our number line. So I'm going to do that in blue next. So let's make our number line for f prime. We have 0 and we have 8. And the other thing I'd like to do here is talk about the behavior of the derivative exactly at each one of these. So 0, we found that by saying where is the derivative undefined. So here I'm going to say above 0, I'm going to just write dne for that derivative does not exist. Our function is actually not differentiable at 0. So we might see some interesting behavior there. 8 is the other point that I want to consider. We found 8 by taking our derivative and setting it equal to 0, so our derivative must be 0 there. And now I'll take a number in each one of these intervals and plug them into my function, my derivative, to determine whether they're positive or negative. So let's start with, how about -1, f prime of -1. This is 1 minus 2 over -1 to the 1/3 power. Here I should have 1 minus 2 over -1. This is 1 minus -2, really, so this is a positive 3. So my function should be, my derivative is positive over here, which means that my function should be increasing on the left-hand side of 0. Next, I need a number to the right of 0, or between 0 and 8. 1 is probably our easiest choice, so I'm going to take f prime of 1. So this will be 1 minus 2 over 1 to the 1/3 power. 1 minus 2 over 1, which is 1 minus 2. This is -1. So my function is decreasing over here because my first derivative is negative there. And then at 8, well, I need a number, I should say, after 8. So a lot of us would pick 9. I see for our derivative, I see this 1/3 power. I know that's a cubed root function. I always like to do as much without a graphing calculator as I can. I'm going to pick 27, f prime of 27, because that's a perfect cube. This is 1 minus 2 over 27 to the 1/3 power. This is 1 minus 2 over 3, which would give me a positive 1/3. So my function is increasing once again because my first derivative is positive. You didn't have to choose 27. You could have just as easily chosen 9 or 10. You would have had to use a graphing calculator to get a decimal approximation in that case. So at this point, we've got a lot of information we can talk about. We know that our function is increasing on -infinity to 0 and 8 to positive infinity. Our function is decreasing between those two, between 0 and 8. And actually, this one's a little bit tricky. We have actually, I shouldn't draw it like that. We have some sort of maximum there at 0. Now I drew that corner and I said, oh, we shouldn't draw the horizontal tangent line because our derivative does not exist. We're going to see some sort of odd behavior happening there. So we're going to have some sort of sharp corner, but I can also look, our domain was -infinity to positive infinity. Our domain was all real numbers. So that means that 0 is included in our domain, which means that there has to be a local maximum at 0. So I'm going to plug 0 into my original function in order to find the y value. So that is x minus 3. So let's see. F of 0, this is 0 minus 3 times 0 to the 2/3. Here I'll have 0 minus 0, which is 0. So I have a local max at 0, 0. So this point right here, again, just to reiterate, even though the derivative does not exist there, we're going to have some sort of maximum occurring. At 8, here, this one's a little bit nicer. This one we're, I think, a little bit more familiar with. We've got the horizontal tangent line. We've got a local minimum at 8. So that means I need to find the y value corresponding to that. I'm going to take that, plug it into my original function. So f of 8, this is 8 minus 3 times, let's see, this will be 8 to the 2/3 power. This is 8 minus 3, this would be, I believe 4. The cubed root is 8 is 2. 2 squared is 4, yes. So that's 8 minus 12 gives me negative 4. So I have a local minimum, we said, at 8 comma negative 4. And that's everything I can get out of the first derivative. I figured out where my function is increasing, I figured out where my function is decreasing, and I've found my local extrema, which means I think we're ready to talk about the second derivative. So my second derivative, let's actually just copy down our first derivative so that we have it ready. Where was our first derivative? 1 minus 2 over x to the 1/3 power. 1 minus 2 over x to the 1/3 power. I don't particularly want to have to do a quotient rule for this term, so I'm going to rewrite that as 1 minus 2x to the negative 1/3 power. Then I think I'm ready to go. I'm going to go ahead and find my second derivative, f double prime of x. So f double prime, derivative of 1, that's just going to be 0. Negative 2 times negative 1/3, that should be positive 2/3 times x, and then I'll subtract 1 from my power. I should have to the negative 4/3 power. Or if I wanted a positive exponent, this is really 2 over 3x to the 4/3 power. So I have my second derivative. I want to identify where is my second derivative, where is f double prime of x equal to 0, and where is f double prime of x undefined, where does it not exist. So f double prime of x is equal to 0. Here in this case, I can just take the numerator, that top part of my function, and set that equal to 0, 2 equals 0. Well, that's silly. 2 does not equal 0. No, I have no solutions to that equation. F double prime of x does not exist. Here that would occur if my denominator is equal to 0. So I'm going to take the denominator, 3x to the 4/3 power, set that equal to 0, and solve this equation. So I'll divide both sides by 3. I have x to the 4/3 power is equal to 0. And then raise each side to the 3/4 power. To the 3/4 power, I have x equals 0. So I have 0 once again. This time, this is the only partition number for my second derivative. So I'm going to construct my number line, just like we have pretty much every other time. So here's my number line for my second derivative, f double prime. We only have 0 on that number line. And I just need to take a number on the left-hand side and the right-hand side, and I'm going to plug that into f double prime of x. So how about f double prime of negative 1? Let's work with that. 2 over 3 times negative 1 to the 4/3 power. This is really 2 over 3. Negative 1 to the 4th would be positive 1. Square root of that would be 1. I'm left with 2/3. So my function is, or excuse me, my second derivative is concave up on the left-hand side, which means that my function is concave upward. And then I need a number on the right-hand side as well. So I will take f double prime of positive 1 this time. So I have 2 over 3 times 1 to the 4/3. Here, once again, I'll end up with 2/3. So my second derivative is positive. My function must be concave up there. So my function is concave up almost everywhere. Oops. My function is concave up. Concave up on negative infinity to 0 and 0 to positive infinity. Be careful here. We actually don't have any inflection points because our second derivative is not changing sign. So we have no inflection points. So here is all of the information I can get out of that second derivative. now I just need to put it all together and make the graph. So let's see what I can remember off the top of my head. We said our domain was negative infinity to positive infinity. We had no vertical asymptotes and no horizontal asymptotes. Our function was increasing. Let's see, where was our function increasing? Negative infinity to 0 and 8 to infinity. Negative infinity to 0 and 8 to infinity. It's decreasing then in between on 0 to 8. We have a minimum, and I forget already. Where's our minimum? 8 comma negative 4. 8 comma negative 4, which means that 0, 0 was our maximum. 0 comma 0. Our graph was concave up on negative infinity to 0 and 0 to positive infinity. And we have no inflection points. Oh boy, okay. Now we just got to make the graph. So here is my, whoops. Let's see, I'm going to look at the points that I have. I have 8 comma negative 4, 0, 0. That's really all I have to work with. I'm just going to make sure that I have plenty of room on that right-hand side. So 1, 2, 3, 4, 5, 6, 7, 8. And actually, I want a little bit more room than that. Let's say 1, 2, 3, 4, 5, 6, 7, 8. There we go. Then 1, 2, 3, 4, 5. There we go. So again, I would recommend starting with your asymptotes if you have any. In this case, we don't. There are no vertical, no horizontal asymptotes. So I'm going to jump down to where are my local extrema. So first of all, we had a minimum at 8 comma negative 4. So 8 comma negative 4. Let's say we had a point, right about here. Also at 8 comma negative 4, remember, and have your sign chart in front of you if you need to, remember that at 8 we had a derivative of 0. We have that horizontal tangent line there. So I'm going to draw in my horizontal tangent line there. Oops. Draw in my horizontal tangent line, and what just happened? Need a point right here, and I have a horizontal tangent line right there. And we know that that is a minimum, so I'm going to label that. We had a maximum at 0, 0, and I don't want to put that horizontal tangent line in because we didn't have a horizontal tangent line. Remember at 0, 0, if I go all the way back, we said our derivative did not exist there. So we don't want a horizontal tangent line. But I will make a note that that is a maximum. And I'm going to look at the concavity here. What's really interesting about this is it's concave up everywhere. It's concave up on negative infinity to 0 and 0 to infinity. So our graph is concave up. It's increasing on negative infinity to 0. So increasing and concave upward, I'm looking at this side of my graph. So let's see. I want to go ahead and erase this part right here. Let's draw this in blue. Our graph is increasing and concave upward. It should look something like this. Be careful here, and one thing I will mention, be careful we don't accidentally draw the rest of the graph. We said it's always increasing on negative infinity to 0, so we want to make sure that our function is always increasing. So perhaps something like this. And then it's concave up on the other side of 0 as well. This is kind of, I think, the interesting part is that it's also concave up over here. So it's concave upward, but on, let's see, this side is decreasing. So it's decreasing. We're thinking about this part right here. It's decreasing until we get to 8. So it's concave up still. Oops. So concave up still until we get to 8, until we get to our local minimum, which is right there. There's our horizontal tangent line. And then after that, we'll draw the rest of the concave up shape. After that, it's going to be concave upward. So it's going to slowly begin to increase, probably something like this. And this this is the behavior that I think is really interesting. We haven't seen a graph like this, at least we haven't sketched a graph like this before. We have not sketched a graph where we have this point right here, this point where it's not differentiable. Our function still exists there, however the derivative does not, and I think that's really, really interesting. So you'll see this a lot with x to the 2/3 power. That's when you most likely have a cusp. If you had, say, the cubed root of x, we might have a point where it's not differentiable, but instead we would have a vertical tangent line. It would be a point of inflection in that case. So you can have some really interesting behavior if your function is not differentiable. You can still have them be, say, local extrema or points of inflection. However, they're not differentiable, which just leads to some interesting behavior, some behavior that we don't always see or don't often see in most functions that we work with.